Hello everyone. In today's lecture, we'll study about the basic physics, that is the part of your CUET-PG. And now in this, we'll study about physical properties and laws of motion. I'm Lisha Patil and let's start. So these are the things that we are going to study today. Its physical properties, उसका temperature, weight and mass, density, refractive index, diffraction and polarization. Then the laws of motion, motion in a uniform field, centripetal acceleration, and motion under a central force. So, our first topic is physical properties. So, our first physical property is temperature. Now, in everyday language, we often say that temperature just tells us how hot or cold an object is. However, in physics, the definition goes much deeper. It says that temperature is an intensive thermodynamic property that quantitatively maps the average translational kinetic energy of the individual molecules or atoms within a macroscopic physical system. So let us break down this highly technical definition into simpler terms. So its intensive property. This means that temperature does not depend on the quantity or amount of matter you have. For example, if you have a boiling bucket of water and you take out a small cup from it, the temperature of the water in the cup will be exactly the same as the water remaining in the bucket. Now, its average translational kinetic energy. The molecules or atoms inside any physical objects are never completely at rest. They are constantly vibrating. They are constantly vibrating, moving, and colliding. This movement is called translational motion. Now, when we measure an object's temperature, we are mathematically mapping the average kinetic energy of this molecular chaos. The faster these molecules move, the higher the temperature becomes. Now, this slide shows that the temperature establishes the baseline criteria for the spontaneous direction of thermal energy transfer, which we know as the heat. Now, according to the zeroth law of thermodynamics, heat energy strictly flows from a thermodynamic state of higher temperature to one of the lower temperature. This spontaneous flow continues until thermal equilibrium is established across the boundaries, meaning the temperature equalize. Think of a hot cup of coffee left on a desk. Now the heat flows out of the hot mug into the cooler room until the coffee reaches room temperature. Now, to record these thermal parameters accurately across physical systems, three classical coordinate scales are mathematically defined. So, the first one is the Kelvin scale. This is the thermodynamic uh, SI base unit. Its absolute origin point is 0K, represents absolute zero. This is a theoretical thermostat where all classical molecular translation and heat emission cease entirely. It is physically impossible to get colder than this point. Now, the second one is the Celsius scale. So, this is an empirical framework built around the phase translations of pure water under standard sea level atmospheric pressure. So, it maps 0 degrees Celsius as the solid liquid melting boundary and 100 degrees Celsius as the liquid gas boiling boundary. And the third one is Fahrenheit scale. This is a legacy empirical scale that divides the exact interval between the melting and the boiling markers of water into precisely 180 equal intervals. Now, now that we understand the baseline physics of these three scales, let us look at the linear transformations used to convert data between them. These exact mathematical equations are crucial for solving the numerical problems. Now, Celsius to Kelvin. If you need to convert Celsius uh, to the SI unit Kelvin, the formula is remarkably straightforward. Please note it down. K is equal to C plus 273.15. For instance, if a room is 25 degrees Celsius, it translates to 25 plus 273.15 is equal to 298.15. That is your Kelvin. Now, if we see Celsius to Fahrenheit, to convert of Celsius to Fahrenheit, we use some of these linear equation. So please note F is equals to 9 by 5 into Celsius plus 32. Alternatively, you can compute it as 1.8 into Celsius plus 32. Now, if we have to convert Fahrenheit to Celsius, we have to rearrange the exact same linear framework allows us to isolate the Celsius variables. So please note uh, Celsius is equals to 5 by 9 into Fahrenheit minus 32. Now, using these equations ensures zero-dimensional calculation errors when transitioning between historical datasets and modern scientific metrics. Now, our next physical property is weight and mass. In classical Newtonian mechanics, mass and weight are fundamentally distinct physical parameters. Conflating or mixing up these two attributes introduces significant dimensional errors into kinetic calculations and structural models. Now, let us contrast them clearly. Mass is an intrinsic, invariant scalar measurement of an object's matter volume. It is direct count of the actual substance contained within the physical body. So, crucially, it dictates the object's resistance to velocity alterations, which is known as inertia. When subjected to an external force vector, a highly massive object requires a much larger force to alter its state of motion because its inertia mass is high. Now, most importantly, mass value stays identical across any spatial region or planetary coordinate system. Your mass on Earth is identical to your mass on the Moon, or in the vacuum or deep space. It does not alter based on the location. Now, our second physical parameter is weight. So, conversely, weight is an extrinsic, highly variable vector quantity. It describes the localized force exerted on a mass by an active gravitational field. It is mathematically derived using Newton's second law, that is, W is equals to mg, where m is mass and g is local gravitational acceleration. Because weight is a vector, it possesses a specific direction. Its vector orientation points along local field lines directly towards the center of gravitational mass. For example, straight down towards the center of the Earth. Since gravitational fields vary across space, for instance, the Moon's gravity is only about 1/6 of Earth's. Your weight will change drastically depending on where you stand, even though your mass remains perfectly constant. Now, our next property is density. Our so it is the density is symbolized by the Greek letter rho. Now, density is an intensive physical parameter defined as the structural mass of a substance packed within a unit volume. Simply put, it tells us how tightly matter is compressed within a given space. Now, analytical importance. Tracking density is a vital metric for monitoring materials purity and characterization across analytical chemistry and material diagnostics. For example, a sample of pure 24-karat gold has a specific density profile. Any foreign impurities or counterfeits will immediately throw this value off. Now, the standard units. The standard SI derivation is expressed as kilograms per cubic meter, though routine laboratory work frequently utilizes grams per cubic centimeter or grams per millimeter. So, it is temperature dependence. Because thermal energy alters atomic spacing, volumetric density depends directly on ambient temperature. When temperature increases, materials typically undergo thermal volume expansion. Since the mass remains constant while the volume expands, This directly lowers their overall density profile. In short, heating a material makes it less dense. Now, we'll transition into the domain of optics with our fourth property, that is the refractive index, denoted by the letter N. The refractive index is a dimensionless optical metric representing how much the propagation velocity of electromagnetic wavefronts slows down inside a medium compared to their baseline velocity in a vacuum. So its mathematical formula is n is equals to c upon v, where c is the speed of light in a vacuum, that is 3 into 10 raised to the power 8 meter per second, and v is the phase velocity of light inside the material. Since light travels at its absolute maximum speed in a vacuum, the value of n for any physical medium will always be greater than 1. Example, we have that n is 1.33 for water and is 1.5 for a standard glass. Now, if we'll see Snell's law, when a light ray encounters a flat boundary separating two media with different refractive indices, the abrupt velocity shift forces the path to bend at a interface. This bending phenomenon is what we call refraction. The angular shift occurs strictly according to Snell's law, which states that n1 sin theta 1 is equal to n2 sin theta 2. Here, theta 1 is the angle of incidence and theta 2 is the angle of refraction. Understanding this, the equation is foundational for designing everything from simple eyeglasses to complex fiber optic communication networks. Now, our next property is diffraction. Diffraction is the bending, spreading, and self-interference of waves, such as light, sound, or electronic beams. When they encounter an obstacle edge, or a slit opening whose size is comparable to the wave's operating wavelength, that is lambda. This wave behavior is elegantly explained by Huygens' principle, which models every single point of an advancing wavefront as an independent source of secondary spherical wavelengths. When light passes through an extremely narrow slit of width, that is A, these independent wavelets spread outwards and begin to overlap and interfere with one another. Instead of projecting a single sharp line of light on a distant screen, this causes the wavelets to create an alternating dark and bright spatial intensity distributing pattern. To map this pattern mathematically, the exact spatial positions of the destructive minima, the dark bands, are calculated using the single slit diffraction equation. That is, A sin theta is equals to m lambda, where A represents the slight aperture width and theta is the angle to the minimum, and m is the non-zero integral representing the diffraction order. That is, m is equals to uh, so we can see that m can be plus 1, plus 2, plus 3, and so on. And lambda is the operating wavelength of the wave. Now, our sixth property is physical property, polarization. So polarization is an optical property unique to transverse waves where the oscillations of the electric field vectors are restricted to a single defined plane perpendicular to the direction of wave propagation. So its critical distinction is longitudinal waves like sound waves cannot be polarized because their physical oscillations always occur parallel to their direction of travel. In natural light, like light from the sun or a light bulb, is completely unpolarized, meaning its electric field vectors oscillates randomly across all possible planes orthogonal to its peak. However, we can linearly polarize it using several mechanical and optical methods, including mechanical filtration, that is dichroic polarites, atmospheric scattering, double refraction that we can call bifurcations, and reflection of flat, non-metallic surfaces. So, if we see Brewster's angle, that is theta b, for so it says that for any given reflective boundary, complete linear polarization occur at a highly unique angle incidence known as Brewer's angle, that is theta b. So the relationship is defined by tan theta b is equals to n2 upon n1. This law is heavily utilized by engineering anti-glare technology, such as polarized glasses, which filter out blinding reflections from horizontal surfaces like water or roads. So now we'll move on to our second topic, that is laws of motion. So in this, first we'll study about the motion in a uniform field. First, what is a uniform field? It describes a spatial region where the force acting on a test object maintains a constant magnitude and vector direction at every single point, regardless of the object's position within that space. A localized gravitational field near the Earth's surface, completely neglecting air resistance, serves as the standard classical model for this, resulting in parabolic projectile motion. Because the vertical and horizontal components of this motion are completely independent of each other, the kinetic trajectory resolves beautifully into separate coordinate components under a constant downward acceleration. So now the first one is horizontal component, that is Ax is equals to 0, the constant velocity, because there is no horizontal force pushing or pulling the projectile. It experiences zero acceleration in the x-axis, maintaining a constant velocity, which is Vx is equals to V0x, and x is equals to x0 plus V0x. Now, the vertical component, that is Ay, is equals to minus g, that is uniform downward acceleration. The gravity acts as a constant downward force, accelerating the objects uniformly towards the ground, which means that Vy is equals to V0y minus gt, or we can say Vy is equals to V0y minus gt. And the final formula can be said is y is equals to y0 plus v0 yt minus half gt squared. By solving these independent linear equations, simultaneously we can precisely model the exact flight path, peak height, and impact point of any projectile. Next, let us analyze the rotational and curve dynamic through centripetal acceleration. When an object moves along a curved path or follows a uniform circular trajectory, its linear velocity vector continuously changes its direction, even if its tangential speed remains perfectly uniform and constant. Now, remember that velocity is a vector. A change in direction means a change in velocity, and a change in velocity over time means an acceleration is taking place. This continuous directional shift requires a net inward acceleration called centripetal acceleration, that is AC, which is always directed radially inward toward the path's center of curvature. The mathematical formulation is given by AC is equals to V square by R gives omega square R, where V is the tangential speed, R represents the turning radius. Now, omega corresponds to the angular velocity component, which is omega gives d theta upon dt. Applying Newton's second law, F is equals to ma, that tells us that if there is an inward centripetal acceleration, a net inward centripetal force, Fc, must act on the mass to sustain this circular motion. Now, we know that Fc is equals to mv square upon r. It is worth noting that centripetal force is not an independent type of force. It is simply a label for which real force, such as friction for a car turning on a track, or gravity for a satellite, pulls an object towards the center. Now, we'll see the motion under a center force. So, a center force is a conservative positional force acting on a particle such that its line of action is constantly directed along a radial line pointing directly towards or away from a fixed point in space, which we call the force center. Furthermore, the magnitude of this force depends solely and exclusively on the scalar radial distance r from the center. Now, Fr is equals to Fr point r. The system operating under central forces possesses a vital conservation property that dramatically signifies their mechanical tracking models. Now, first one is the conservation of angular momentum, which is L. The torque acting on a particle is defined as the cross product of its position vector and the force vector applied to it. We know that torque is equals to R into F because a central force acting perfectly parallel or anti-parallel to the radial position vector, their mathematical cross product is identically zero. Now we know that torque is equals to R into FRR is 0 since torque represents the time derivative of angular momentum, which is torque is equals to dl by dt. A net torque of 0 proves definitively that the angular momentum vector L remains completely constant over the time, which shows that L is constant. This conservation rule is an extraordinary mathematical tool for astronomy and orbital mechanics. Now, building upon the conservation of angular momentum, we arrive at our final mechanical insight. Because L is proven to be entirely constant in both magnitude and direction, the position vector r and the linear momentum vector p must always remain confined within a fixed, unchanging two-dimensional plane that sits perpendicular to L. This proves a foundational law of physics. All motion under a central force is restricted to a single flat orbital plane. The object can never break out into three-dimensional drifting. Its entire motion is locked to a single flat sheet of space. This is the exact principle that governs planetary orbits and satellite paths operating under inverse square gravitational fields, which is F is directly proportional to 1 by r square. It explains why our solar system's planet orbits the sun in the remarkably flat disk-like plane. So now, and that brings us to the conclusion of our basic physics part 1. We have transferred uh, we have traversed the landscape of physics today, starting from the microscopic kinetic energy of temperature, moving through the wave behaviors of diffraction and polarization, and finally exploring the massive microscopic laws of planetary orbits governed by the central forces. So, I highly recommend you to review these linear equations and properties to build a strong foundation for our next session. Thank you very much for your time and attention. Thank you so much.